So I will, the title of the talk is Reaction Dynamics with Neutron Proton Beams. This is the outline. I will make a brief presentation of nuclear structure of light exotic nuclei. And in particular, I will discuss during talk of the interface between the structure and the reaction dynamics, in particular, highlighting the results that we have achieved over the years in the studies with the neutron beams. I will briefly show you the new results that we have got in an experiment we made in the year 2019 BC before COVID with lithium-11 beam at Triumph, and the new results of the experiment that we performed with the proton halo beam boronate at Isolde using for the first time post-accelerated boronate beam. Then I will make my conclusion. So light nuclei are a special case. The quantum mechanics play a role in creating many different peculiar structures, as for example, cluster structures of different types. These are present in the excited state of many of light nuclei, but in some cases also in the ground state, as for example in the lithium-6 and lithium-7 or beryllium-9 case. Especially at low energy, but in general, all these structural features have some effect, of course, into the reaction process. Experimentally, the challenge has been in using beams, measuring cross-section with beams, in some cases with extremely low intensity. And from a theoretical point of view, has been including all these different structures into the reaction dynamics in order to properly describe the measured quantities. Just an example of such a peculiar structure of I'm talking about is the beryllium-11 case. This is a 1 neutron halo nucleus. It's extremely weakly bound. The binding energy is only 500 keV. It has a bound excited state, bound by only 300 keV, and it has an extremely large radius. The halo radius is about 7 Fermi, and the dipole transition between the first and the ground state, first excited state and the ground state, is the strongest known electric dipole transition between two bound states. And moreover, it has, as other halo nuclei have, like lithium-11 or helium-6, a large non-resonant dipole strength above threshold. All these aspects may in some way influence the reaction dynamics. For example, the large B1 means that nuclei are easily to polarize, and so in the Coulomb interaction with a heavy target, for example, they break up. This breakup could be favored also by the fact that the nuclei are weakly bound, and also the extension of this the large radius may affect the different process, as for example fusion, but also, as I will show you, elastic scattering. At low energy, one has to, in order to calculate the reaction process, to consider the coupling between the relative motion and the intrinsic excitation of the nuclei of both projectile and target, which in the case of weakly bound nuclei and halo nuclei means including the coupling to the continuum. And this is done via the continuum discretized couple channel calculations. I divided the talk into 3 chapters where I discuss the main feature of the 3 main reaction processes that have been investigated so far. The first is the elastic scattering. This is, of course, elastic cross-section is large, so it is easier. I'm not there to say that it's easy, but it's easier to measure elastic scattering cross-section. I will show you the main results that have been, let's say, the main highlights that have been achieved. In the case of, for example, lithium-11 on lead, what it was observed is a large suppression of the elastic cross-section. Here is the comparison is done with the lithium-9 on lead, that is a weakly bound nucleus. So there is a large suppression of the elastic cross-section below and above the barrier. You see the elastic cross-section in the lithium-9 is very much reduced. This means also an extremely large total reaction cross-section. In this case, this high reaction cross-section is due to the breakup, to the breakage channel, due to the large B1 strength of non-resonant strength of the lithium-11. On a lighter target, on a medium mass target, nuclear effects are equally important. So there is again a suppression of the elastic cross-section, but this suppression has been observed mainly in the nuclear Coulomb interference region. So rather than having a peak due to the interference between the Coulomb and nuclear amplitudes, we have a dip. Such a feature had been observed already in reaction with stable nuclei and was attributed to long-range absorption, which in this case was the Coulomb excitation of the quadruple state of the deformed target. While in the beryllium-11 studies, this long-range absorption is due to both Coulomb breakup, but also to nuclear breakup. This was studied in this paper here that we published in 2012. And this long-range nuclear interaction is due to the extended surface of the beryllium-11. In fact, in order to describe the data within the optical model, we had to include a surface term having a very large diffuseness. Some other information that we learn is the relevance of the core excitation effects. In fact, beryllium-11, but also lithium-11, have a deformed core. So the excitation of the core, the dynamic excitation of the core degree of freedom, as well as the halo degree of freedom, had to be accounted for to describe the measured cross-section. This can be seen here are the results of a TRIUMPH experiment with the beryllium-11 beam when it was used coupled with the silicon detector to measure the charged particles, Tigris, the gamma ray detector. So it was measured the excitation of the first excited state of beryllium-11. As you see, both elastic and inelastic cross-section, in order to be properly described, needs to include the core excitation effects. The effect is dramatic in the case of inelastic cross-section, while, for example, in the case of a breakup, as I will show you, the effect is very small. Lithium-11 is also, it is a 2-neutron nucleus, is also very weakly bound. And in addition to the features that I had just described for beryllium-11, it has also a soft dipole resonance. This was discovered in a TRIUMPH experiment here. And this resonance is at about 800 kV and is due to the collective motion of the neutrons of the halo with respect to the lithium-10 core. Also, the presence of this resonance, as it was found, for example, in the elastic study of lithium-11 on lead, influences the reaction process, in particular the elastic scattering process. And since at TRIUMPH it is available a very nice lithium-11 beam, we decided to complete our investigation on zinc-64 target, extending the studies to lithium-11. We had studied helium-6, beryllium-11, and now in 2019 we also studied the lithium-11 scattering. The data are still preliminary, very preliminary, so the data analysis is ongoing. Anyhow, one can see that the elastic cross-section is strongly suppressed, as it was the case of the beryllium-11, And in fact, here is shown the comparison of the lithium-10 angular distribution and the beryllium-11, lithium-11 angular distribution and the beryllium-11 angular distribution. They look similar. Maybe the lithium-11 case is even more suppressed, while this is the case of the helium-6, where there is a clear Coulomb nuclear interference peak. We have also the breakup data, as we can see here. The lithium-9 and lithium-11 could be separated, lithium-9 coming from the breakup. Again, this is just to show that still work is in progress. We are also extracting the data on the breakup in this case. Concerning proton halo, this is not as common as neutron halo. One of the candidates of a proton halo structure is boron 8, which is an extremely weakly bound nucleus. The binding energy is only 130 keV. However, the valence particle is a proton, so it is a charged particle, and is a P-wave proton. So the Coulomb, as well as centrifugal barriers, may inhibit the existence of a halo. And this was widely discussed in the literature. A recent experiment performed at GSI has shown, though, that the matter density distribution for boron 8 seems indeed to be to show a tail. This is the comparison of the boron 8 and the lithium 8 matter density distribution, which would be compatible with the existence of a halo. The question is whether the presence of this halo in the boron 8 shows up in the same way as in the case of neutron halo in the reaction with in the interaction with the target. We do not expect to see the same features. For example, we expect the existence of polarization effects, and due to this, the valence proton is expected to be displaced behind the core, and so, for example, the breakup would be reduced with respect to the first order perturbation theory. There is a semi-classical calculation performed by Angela and Kumar, where the different contribution of the interaction are highlighted. Of course, being a semi-classical model, it is the calculation are performed at high energy. But I found this nice because somehow one can visualize what is going on. The Coulomb interaction of the proton halo nucleus and the target has two terms. The recoil term, that is the core target interaction, and the direct term, that is the proton target interaction. This is the parallel momentum distribution of the boron 8 breakup. And you see that the recoil term, that will be the same as for the neutron halo, it is smaller than the direct term. The two, of course, interfere, and the interference depends on the target, but also on the energy. So it is constructive in the case of carbon 12 and destructive in the case of the lead target. In addition to this, there is the nuclear interaction that again interfere with the Coulomb interaction. So overall, we have an effect that depends on the target and on energy. Here is again a semi-classical calculation done by Angela. And what can be seen is that the recoil term, in the case of a proton halo, is similar to that of a nuclear, is the same as that of a neutron halo, but just with a higher binding energy. However, the direct term is the one that dominates. This is the angular distribution for the proton coming from the breakup of the boron 8, calculated proton angular distribution. If we go to lower energy, which is the energy range where we have performed our studies, things get complicated and one needs to perform a couple channel calculation. And here, this calculation were performed by Young and collaborators, who studied the effect in elastic scattering of boronate on our preferred zinc 64 target. And you see the red line and the blue line is the predicted angular distribution considering the full calculation, so the coupling with the continuum and without the continuum coupling. And you see the effect, the expected effect in the case of boronate is very small, opposite to what was observed for the beryllium-11 on the zinc target. However, if one would switch off the Coulomb interaction of the proton, we would have observed a suppression, which would be even stronger if the Coulomb interaction would be switched off. So basically, the behavior of the boronate interaction with the target, similarly to what found by the Angeles calculation at high energy, depends on the Coulomb and centrifugal interaction of the proton, of the valence proton in the boronate. From an experimental point of view, well, boronate is a difficult beam to be made in as a post-accelerated beam. And in fact, almost all experiments were done with the in-flight produced beam. These are the results that were obtained at Vibres of boronate on aluminum at 2 energies. And in this case, what is observed is what I've just shown you. There is a small, very little effect, very little different, not considering coupling to the continuum. And the total reaction cross-section is found to be similar as other weakly bound nuclei like lithium-6, lithium-7, and so on. Different was the situation with the boronate on nickel, where this experiment was performed in Notre Dame at 5 energies. And from the optical model analysis of boronate on nickel, what they deduced, what the author deduced was an enhancement of the total reaction cross-section, which is shown here, but it was found to be much larger than that of the weakly bound, other weakly bound nuclei on similar targets. Although the analysis done here with CDCC by Lubian and others actually doesn't find a very large difference of considering and not considering coupling to the continuum. A similar result was found for boronate on lead. This experiment was performed at CIRI Barrican by Marco Mazzocco and collaborators. Again, it was found a very large total reaction cross-section, much larger than for the others. However, an experiment that had been performed at Lanzhou with boronate on lead, so on the same target, but at higher energy, it is here shown, didn't produce the same results. In fact, the cross-section, the elastic cross-section, which here is compared with lithium-6 and beryllium-7, looks very similar. Maybe the difference is that this is a higher energy, where coupling effects are expected to be smaller, while the previous experiment was done at lower energies. However, the calculation that are shown here for the lead and the zinc target at 2 different energies, at high energy and at low energy, seem to be similar, to show similar results, and here compared with what is expected for beryllium-11. So many years ago now, I think it was 2004, when we asked for the development of an ISO boronate beam at Isolde. But this is a tough beam, so it took a while, but in the end, they succeeded. So it's now available at Isolde, a post-accelerated boronate beam. The quality of this beam is, of course, excellent. The purity was better than 99%, and the energy resolution is limited. Basically, the target of the experiment is limited by the target that you are using. Unfortunately, there was a problem. So the beam intensity for this experiment, it was the first experiment with this post-accelerated boronate, was limited because of a stable contaminant that was unforeseen, and so we lost a factor of probably 10 or more in the actually beam intensity that we could have. The intensity was only 400 particles per second. Nonetheless, we could measure very nice elastic scattering angular distribution that is shown here, and mapping the Coulomb nuclear interference region very carefully, and with an angular step that is 1 degree at small angles and 2 degrees at larger angles. And you see that the effect is confirmed that it is very small due to the continuum coupling. So a different result than for beryllium-11. This is the optical model analysis. The calculation are done with an optical potential derived from lithium-7 on the same target, and no need for an extra surface term was required. If we compare the boron-8 angular distribution with the beryllium-11 that is shown here in blue, we see that very different behavior. While if we compare with the beryllium-9, we see that the boron-11 and beryllium-9 look very similar. These are the similar central mass energy with respect to the Coulomb barrier. The total reaction cross-section is around 1.5 bar, similar again of that of beryllium-9 on zinc, and is about half the total reaction cross-section that we got for the case of the beryllium-11 case. So the strong effects that we observed in the case of neutron are not do not show up in the case of the boron-8, proton-halo boron-8. Now let's go to discuss the second chapter, where I show you the results concerning breakup. Most of these experiments are inclusive breakup measurement, where the only one of the fragments is detected. This because, okay, in the case of a neutron-halo reaction, the other particle, the other partner is a neutron, so it's very difficult to measure, especially if you have low intensity beams. This would be possible in case of the boron. Unfortunately, in our case, the beam intensity was too low, so we didn't see in the end coincidences. Anyhow, in order to be able to describe the data, we need to include all processes. So the elastic breakup is calculated with the CDCC calculation, while for the data I'm going to show you, the calculation were done using the EF model that was discussed a couple of weeks ago by Antonio in his talk, so I'm not going to add anything on that. Anyway, one needs to consider all possible processes, like inelastic excitation of the target, or the transfer of the halo particle or the incomplete fusion needs to be included to compare with the data. In the case of beryllium-11, so neutron-halo nuclei on every target, the dominant process, as I mentioned before, is the Coulomb excitation. So the breakup is dominated by the elastic breakup process. Also, core excitation effect in the case of breakup channel are very small. The non-elastic breakup contribution here is negligible. The situation changes when we have a lighter target, as for example in our zinc measurement. Elastic breakup as well as non-elastic breakup contribution, it's both to be considered. And in fact, at large angles, these are the energy distributions. At large angles, they are equally important. A feature that we observed, for example, in this experiment here, was the post-acceleration effect. So the beryllium-10 core gets accelerated after breaking up. This means that the breakup is a near target breakup, is not an asymptotic breakup. Different was the situation that we found in the case of helium-6. The dominant contribution is not the elastic breakup as for the previous two cases, but is the two-neutron transfer. You see, this is the angular distribution of the alpha core, and we see that, okay, except for the highest energy where the elastic breakup becomes important, at low energy, the non-elastic breakup is, especially at very low energy, is dominating the cross-section. And in particular, with CRC calculation, it seems that the dominant reaction mechanism is the two-neutron transfer. Let's see what we measured with the boronates. The breakup cross-section looks smaller than for the beryllium-11. But also in this case, elastic breakup as well as non-elastic breakup, they both contribute. This is the breakup probability, and as we can see here, the non-elastic breakup contributes at largest angles, becomes dominant. Here we can see the 2D plot where we see the elastic, the beryllium-7. And so the alpha particles, protons are down here, they are cut in this spectrum. If we look at the energy distribution, so this is the beryllium-7 energy distribution, we see that they are very nicely reproduced by the CDCC plus NEB calculations. You see at largest angles, the NEB become non-elastic breakup become dominant. And here it seems that there is a different feature that what we observed in the case of beryllium-11. It seems that this is the calculation for no post-acceleration and post-acceleration, that in this particular case is a de-acceleration. It seems that the energy distribution is more consistent with no post-acceleration situation, so with an asymptotic breakup. However, if we perform an analysis similar to what was done by Filomena Nunes and Tosteven for boronate and nickel, so we analyzed the various contribution to the breakup. So that is the Coulomb of different multipolarities, not just the dipole as for beryllium-11, but also higher multiples. And these various multipolarities deform the spectrum, they interfere. And in addition to that, there is also the nuclear contribution. So overall, the shape of the energy distribution depends on the combination of all these effects. So they don't give an information. The actual position of the energy distribution does not give information on post-acceleration and on the fact that the target is near target or asymptotic. Our guess is that if only the Coulomb dipole would have been relevant in the case of boronate, we would have observed the de-acceleration. At least this was the calculation we showed. But as I said, the overall effect, it's to wash out the post-acceleration effect. Now, I will go to my last chapter, that is discussing fusion. This is really, I mean, in this part, I don't want to draw any conclusion, but I just want to give some message. And just to, because it is to measure fusion with this beams, it's stuff we have done in the past with helium-6, and it is not an easy task. And I want to, with this, what I'm going to show you in a minute, I just want to send some messages, especially to experimentalists, to be careful when performing such measurement. In the case of proton halo, a large enhancement of the fusion cross-section. This was the same story also for neutron, but just using this to introduce what I'm going to say next. A large enhancement of the fusion cross-section was claimed. These are the data of boronate on nickel. In this case, the signature for the fusion process was the emission of protons and alpha. So the fusion cross-section was determined by measuring protons and alphas and using statistical model calculation to deduce the total fusion cross-section. The beam was an in-flight beam at Notre Dame, so with an energy spread of about 1 MeV. And in order especially to measure the low energy points, the targets that were used were extremely thick targets. A follow-up measurement by Tina Pacu in Padova, where they measured boron 8 on silicon using the active target techniques are completely different technique, but the signature for the fusion process was the emission of alpha particles. They don't seem to confirm these strong enhancement results. These are the data of boron, which are similar to the other reaction with neutron nuclei, where such an enhancement was not observed. A recent visitation of this data done by Aguilera using different statistical model codes to reevaluate all multiplicity and because one of the questions was that what if the charged particle multiplicity is not properly calculated? And this will give you a wrong information on the fusion cross-section. So he reanalyzed all data with different codes and also reanalyzed the boron on silicon. In the end, the conclusion was the same. So they didn't really change the fusion cross-section values, and using different multiplicity for the alpha particles in the case of silicon, the results were closer to the one of nickel and looked more consistent with the nickel data. What I want to point out now is a problem that is always, well, I would say always overlooked when doing this type of experiments. So fusion excitation function measurement with low intensity beam having a high energy spread and using a very extremely thick target. This problem was highlighted, discussed in detail by us in this paper. And I'm trying to summarize what the conclusion of this work was. When we measure fusion excitation function, so a strongly varying cross-section with varying with the energy, we may have some problem. The results are affected by 3 factors: the beam energy spread, which is the first factor, the energy loss of the beam in the target. So in the end, you end up with an energy distribution inside the target, which looks something like this. But also, you may have problem of target non-uniformity. This was the case of an experiment we performed with lithium 6 and 7 using thin target. This is a photo of our target, that huge non-uniformity. So in the end, your energy distribution is affected by these 3 factors. What people normally, so the experimental datum is the mean cross-section. So what we measure is a mean cross-section. And this cross-section is averaged over a certain energy distribution that, as I said before, is the convolution of these 3 factors: beam energy spread, beam energy loss in the target, and also target non-uniformity. So this is our experimental observable. Then we need to plot an excitation function. So we need to associate to this experimental cross-section and energy. Normally, well, one can associate the mean energy, that is the energy at the center of the target, or in the case of the very thick target, so where the cross-section changes a lot in the region where we are going to average the cross-section, people use the effective energy, that is the weighted mean. So weighted with the cross-section. And in this work, we added an additional term, that is the energy distribution. So the probability of having a given energy at a given thickness, a particle with a given energy at a given thickness. Normally, this is not considered in the determination of the effective energy, but just the cross-section that is unknown. So people use this iterative procedure to deduce this effective cross-section. Well, in this work, we found out that either you use this technique, this method, so to plot the mean cross-section as a function of mean energy, or you use the effective energy. If the energy loss in the target, if these effects are large, you're not doing the correct thing. And this is shown here. We have an analytical function as cross-section, so it's a Wong type of function. And we calculate, so we can calculate the mean energy, also given an energy distribution inside your target. We can calculate the mean cross-section by integrating this function, and also the effective energy. Well, if we plot the mean cross-section as a function of the effective energy or of the mean energy, if the energy loss in the target, this effect I've mentioned are large, you get the wrong excitation function, as is shown here. The initial function is the black line, while the points give you the excitation function determined using the effective energy, and the open symbols are is the excitation function you obtain using the mean energy. And if we look here in detail, the effect of the beam energy resolution in particular, we see that if you have a broad beam, so a beam with a poor energy resolution, you would associate the mean cross-section to a position that has nothing to do with the real excitation function that is here shown with the line here. So one has to be very careful experimentally when one deduces the strongly varying cross-section averaged over a wide energy range. We propose a solution to this problem that is using a convolution procedure. In fact, the result of the convolution is the blue line here, as you see, is consistent with the initial function with an error bar, that is the light blue shade here. And the error depends on the experiment, no? So it depends on the error on the main cross-section, but also depends on the number of points that you have to reconstruct the excitation function. So I wanted to, as I said, this is very often overlooked. The people that don't consider these problems when they perform this type of experiments. And now, briefly, to our boronate and zinc data, we also have protons and alpha particles. And so we are analyzing them, but still we don't understand them very much. So here is shown the angular distribution of protons, which looks rather flat. So we could have concluded, maybe we could conclude that we have only fusion evaporation processes, because in these data are compared with the calculation made with PACE 4, so statistical model calculation. The shape looks consistent with statistical model calculation. However, we know that we have protons coming from elastic breakup, because we do see beryllium 7, so we must have protons. And here are shown the CDCC calculation for elastic breakup are shown here. So there is something that we don't understand. Maybe there is a problem with the data. We are checking whether we have a threshold. So we are cutting events, for example, at small angles. We haven't found the origin of the problem yet, but maybe there is. Anyhow, we know that there are other sources that are producing protons. So there can be complete fusion, but there is also the breakup. And an additional source of protons could be the transfer, or let's say incomplete fusion of the protons with the target. This will produce a gallium-65 that is excited and is above particle emission threshold. So will re-emit a proton with almost isotropic angular distribution as for the complete fusion reaction. The energy distribution of protons is at forward angles is not consistent with fusion evaporation. There is for sure the contribution of the elastic breakup and probably something else. And the backward angles shape is more similar to a statistical model calculation, as can be seen here, but maybe there is also here something else. So light particles are, to my opinion, not a good probe for measuring fusion, because it is difficult to understand the origin of this particle. Same situation is for the alpha particles. The angular distribution is shown here. The alpha yield is extremely low, extremely small. We don't see any alphas at very forward angles. And the angular distribution doesn't look consistent with the fusion evaporation calculation. This is at phase 4, we're using the same normalization that was used for the protons, that was normalized at backward angles here. And we know that there are other sources of alpha particles, also in this case, that is the 3-body breakup, and also could be the fusion of helium-3, which leaves lithium-5, which decays in turn in helium-4 plus P. So again, the message is, okay, with the protons and alpha, one has to be really careful to draw conclusion, to my opinion. If we use this normalization, the phase 4 calculation normalized that backward emitted protons, we would get a cross-section that is here. I'm not claiming any reduction or suppression of the cross-section or anything. Just I wanted to send a message, and is that, okay, we, as I said before, it is difficult to understand which process is originating the protons and alpha particles. So one has to be careful. And I just found this paper that is very recent, where the active target was used, so it's boronate and argon at Texas A&M. And in this case, it doesn't seem that there is any enhancement of the cross-section for the boronate-based reaction. So I hope I have not bothered you so much in discussing the main results of the reaction studies that have been performed with neutron nuclei and the new progress that have been made with the investigation of proton nuclei, which behave differently than neutron halo. What next to be done? Well, if we would have a higher intensity beam, we could make more precise measurement, and also perform exclusive measurement, where the coincidences between different fragments, for example, coming from breakup, could be measured. And also, still from a theoretical point of view, there are still some type of calculation, like for example, co-excitation of the two neutronal nuclei, which are still out of reach, I believe. So there's still some work to do, and well, let's see what we can do in the future. And with this, I thank you, and I've finished.